Hello everybody and welcome to this ISSCC 2022 tutorial on analog circuit design in BCD technologies. Let me first introduce myself. My name is Marco Berghout. I received my master's and PhD degrees from the University of Twente in the Netherlands in 1992 and 96. After that I joined Philips Semiconductors that later became NXP, and in 2020 I joined Goodix Technology. In the 25 years of my career, I have worked on Class D audio power amplifiers for home, automotive and mobile applications. I hold more than 25 patents and was author or co-author on 20 plus journal and conference papers. From 2008 to 2018, I served in the TPC of the European Solid State Circuits Conference, and from 2013 to 2016, I joined the TPC of ISSCC and rejoined again in 2020. Before we start the tutorial, I would like to point your attention to this. On May 18, 2021, the invention of BCD technology was commemorated with an IEEE milestone. IEEE milestones honor significant technical achievements in all areas associated with IEEE, and the invention of BCD technology has joined the ranks of other iconic inventions, such as, for example, the SPICE circuit simulator, the floating gate EEPROM, Wi-Fi, CDMA, and last but not least, Moore's Law. Chips made with BCD technology can be found in many devices that we use on a daily basis. When you charge your battery or your phone through a USB cable or wirelessly, you are using BCD technology. The device that connects your solar panels to the mains also uses BCD technology. Cars are packed with ever-increasing amounts of BCD chips, driving the motors of the windscreen wipers, the windows, and even the drivetrain in electrical vehicles, or control the LEDs in those fancy LED matrix headlights. And also at home, you cannot get around BCD, where it is used for audio, lighting, and display drivers of your TV and laptop, and even induction cooking. BCD technology can basically be found anywhere where electrical power is converted to motion, light, sound, heat, or simply another form of electrical energy. BCD technology combines analog, digital, and power devices on a single piece of silicon. With analog, we can build complex feedback loops, accurate references, and perform advanced signal processing with high speed and accuracy. With digital cells and high density, we can make control logic, standard interfaces, and DSPs. And as a rule of thumb, CMOS density in BCD lags about 10 years behind the most advanced CMOS nodes. At this moment, 40 nanometer BCD is emerging. And to top it off, BCD features power devices that allow high voltages and currents on chip. So what do I mean with high voltage? Well, from a circuit design perspective, high voltage means any voltage high enough to damage the gate oxide of your MOSFETs. In practice, the voltage depends on the application area and goes from 8 to 20 volts for mobile up to as high as 6 kilovolts for galvanic isolation. And optimized BCD process nodes are developed for each voltage range. High on-chip voltage comes at the price of silicon area. The voltage needs to be distributed over a certain distance to prevent the electrical field strength from reaching critical values. So for a higher breakdown voltage, we need more distance between device terminals, but also more space for isolation barriers between devices. So what is then considered a high current? Again, from a circuit design perspective, high current is any current that causes significant conduction loss. On-chip currents are in the 1 to 5 amps range in battery charges for power management for mobile devices, but can also reach several tens of amps in high-power audio amplifiers and motor drivers. Such high currents need solid low-ohmic connections that are made possible by dedicated process and package features such as ultra-thick copper metallization, thick parallel bond wires, and bonding on active area. And to give you a flavor, the picture on the right shows a 5-channel Class D audio amplifier that has more than 100 bond wires connecting the power supplies and outputs. After this short introduction and motivation, Here's the outline of this tutorial. Next up, we'll have a look at the structure of BCD technologies and their constituent devices. Then we'll discuss critical device characteristics and the figures of merit used to benchmark BCD technologies. After that, we'll have a look at classic applications and identify their commonalities. And finally, we'll dive into circuit design and design techniques. So let's start with the technology and devices. The acronym BCD stands for Bipolar, CMOS and DMOS. These three device classes were developed separately, but were first combined into a single process technology by ST Microelectronics in 1986 and was described in a seminal paper in the IEEE Transactions on Electron Devices. As I mentioned at the start, this invention is widely recognized as a milestone in the history of technology. To understand how these device classes are combined, we'll have a closer look at them one by one, starting with CMOS, which I expect is the best known to most of you. CMOS is a combination of N and P-type MOS transistors as illustrated in this cross-section. The NMOS is made in a P-well and PMOS in an N-well, and their source and drain diffusions are masked by a polysilicon gate on a thin gate oxide. Both NMOS and PMOS are symmetrical, meaning the source and drain are interchangeable, and usually the wells are shared by multiple devices, which enables very compact layouts and high device density. The many PN junctions present in CMOS are usually either shorted or reverse biased, so in circuit design you typically don't worry about them too much. That is, assuming you do a proper job in connecting the wells. The combination of PN junctions also form parasitic bipolar transistors, as indicated here, that can get stuck in a positive feedback loop. And this causes a phenomenon known as latch-up. When we redraw the parasitic circuit a bit, a circuit emerges where two bipolar transistors turn each other on, causing a current from supply to ground. The best way to prevent this from happening is to make sure the resistances in the circuit are small, and this is achieved by adding sufficient contacts to the wells. And this is covered by layout design rules that specify the maximal distance between the well connections. In digital layout, these well connections are part of the standard cells or they are inserted by layout tools, so essentially they're correct by construction. And in analog layout, it is common practice to place the well contacts as rings around the devices as illustrated here on the right. In standard CMOS, the P-wells are connected to the substrate, and it makes the NMOS sensitive to substrate disturbances. This connection to substrate is severed in so-called triple well CMOS by adding a deep N-well. A deep N-well is a high-energy implant that creates a highly doped barrier below the P-well without affecting the behavior of the devices at the surface. The P-well is now isolated and allows the NMOS to be biased at a higher voltage than the substrate. Next, let's have a look at bipolar transistors. The term bipolar means that both electrons and holes are involved in the operation of the transistor. The bipolar junction transistor has three regions with different dopant levels as illustrated here. There's a heavily doped emitter on the left, a lightly doped collector on the right, and they are separated by a narrow, moderately doped base of opposite polarity. This creates two PN junctions with associated space charge regions. There are two complementary types. Shown here is an NPN, named after the polarity of the emitter base and collector, but we can also swap the polarities and make a PNP. In normal operation, the base emitter junction is forward biased. This results in a large flow of electrons from emitter to base and a small flow of holes in the other direction. The base collector junction is reverse biased, and all electrons that reach the space charge region are swept away and flow towards the collector, whereas only a few electrons recombine in the base. This results in a high current gain, which is the ratio between the collector current and the base current, and typically the current gain is in the range from 50 to 200 times. In process technology, the bipolar transistor is realized vertically by adding a p-body diffusion to the diffusions we already know from CMOS. This p-body diffusion forms the base of the transistor, and the width of the base region is now determined by the difference in vertical diffusion between the p-body and the n+ diffusion that forms the emitter. The graph on the right shows the doping profile in the vertical direction along the dotted line, while with a heavily doped n+ emitter, a moderately doped p-type base, and a lightly doped n-type collector, and this is exactly the profile needed to get a high current gain. The high dope at the bottom of the p-well helps to make a low ohmic connection to the collector contact at the surface. The third and last component of BCD technology is the DMOS transistor. The DMOS transistor is built with the same diffusion as the bipolar transistor in combination with a MOS gate. The D in DMOS is short for double diffused, and this refers to the two diffusions that form the source and the body of the transistor that are self-aligned by the gate. This creates a channel region underneath the gate that has a length determined by the difference in lateral diffusion between the p-body and the n+ source. The length of the resulting channel does not depend on the length of the gate, so only the width of the channel can be scaled. The distinctive feature of DMOS transistors is that they can handle a drain source voltage that is much higher than the maximum gate source voltage. This is made possible by the so-called drift region, which is a lightly doped region between the end of the channel and the drain contact, and that acts as a buffer between the channel and the drain. Because the drift region is in series with the channel, it also determines the on resistance between the drain and the source when the DMOS is turned on. In a typical DMOS device, the gate extends over the drift region on a thick oxide that creates a characteristic stepped profile. This gate extension helps to reduce the electric field at the surface of the device. And we use the deep end well for isolation. In contrast to CMOS, DMOS transistors are asymmetrical, which means the drain and source are not interchangeable. Furthermore, when we examine the doping profile in the lateral direction along the dashed line, we see that this is actually very similar to that of the bipolar transistor, and consequently, DMOS devices inherently have a very effective bipolar parasitic. In order to prevent this bipolar parasitic from being activated, the source and body of the DMOS are always shorted together and considered as a single terminal. This means that there is always a diode between the source and the drain. In the bottom right shows some examples of symbols used for DMOS in literature. They all explicitly show the drain to source diode and something to mark the drift region, and sometimes even the gate step. In this tutorial, I will be using the version in the red box on the left. A simple model of the DMOS is a regular NMOS and a JFET cascode, where the pinch-off of the JFET limits the internal drain voltage as seen by the NMOS. In parallel, there is a drain source diode that requires a proper characterization of the forward conduction. And there we have it. As we have seen, the bipolar CMOS and DMOS transistors use the same diffusions, so they can be combined side by side in the same silicon substrate to yield BCD technology as illustrated here in its simplest form. The devices are isolated from each other with p-well barriers, and the spacing in between scales with the required voltage difference. You may have noticed that the DMOS device that was presented is an NMOS type. So a straightforward question is, what about high voltage PMOS? In principle, it is possible to make a p-type DMOS, but this is unusual because p-type devices have a higher on-state resistance due to the lower mobility of holes compared to electrons, and this makes them more expensive. You basically need a bigger device to get the same on resistance. And on top of that, you would need additional diffusions to make a p-type DMOS, which also adds to the cost. What we can build without adding diffusions is a so-called extended drain PMOS. In this device, we extend the drain of a standard PMOS with a drift region made from p-well. Also, we extend the gate with a stepped field plate and use the deep end well for substrate isolation. Actually, with these same diffusions, we can also make a complementary extended drain NMOS. And as you can see, these devices only use elements from the triple well CMOS and enable high voltage derivatives of standard CMOS technologies. Such technologies are cheaper than BCD because you don't need the body diffusion used for bipolar and DMOS transistors. However, the on-state resistance of these devices is higher than DMOS, so they are not suitable for high power applications, but can be attractive in applications where only high voltage is enough. Some short remarks on the terminology of folding. Folding is used to create transistors with a very wide gate and an acceptable aspect ratio. There are two flavors. We either mirror around the drain, which is called drain-centered, or around the source, which is called source-centered. And typically for large power FETs, we fold many times. For example, even more than 100 times folding is no exception. In such a folded structure, we define the pitch as the distance between the center of the source and the center of the drain. And now you can calculate the net area of a power FET by multiplying the pitch and the gate width independent of the number of folds, but this of course excludes the additional area needed for lateral isolation. Some words on isolation. We already discussed the drain source diode that is an inherent part of DMOS. But this is not the only diode we need to be aware of. When we use deep N-well to isolate the source from the substrate, we also add a diode between the drain and the substrate, as illustrated here. When the drain is pulled below the substrate, which is actually quite common with inductive loads, this diode becomes forward biased and injects electrons into the substrate. Electrons are minority carriers in a p-type substrate, and they can trigger latch-up if they surface in other parts of the circuit. To avoid this, DMOS devices are usually surrounded by N-type guard rings that aim to collect the injected electrons. In this collection mechanism is made more effective if the guard ring is connected to a positive voltage. To complicate matters, the deep N-well also creates a parasitic PNP transistor, where the P body is the emitter, the deep N-well is the base, and the substrate is the collector. When the source of the DMOS is pulled higher than the drain, and again this is quite common with inductive loads, the base emitter junction becomes forward biased, injecting holes into the deep N-well, and a significant fraction of these holes ends up being collected in the substrate. Because there is usually a large voltage difference between the deep N-well and the substrate, this gives rise to high dissipation. The holes can raise the local substrate potential, and this can cause problems in neighboring circuits. To avoid this, DMOS transistors are also surrounded by p-type guard rings to firmly fix the substrate potential at the periphery. Obviously, the guard rings increase the silicon area used by the DMOS, and this area increases with higher voltages. This illustration shows a typical example layout of a small drain-centered DMOS device with the N-guard and P-guard rings. And as you can see, the effective area is about 10 times that of the net device. Clearly, the area penalty is relatively large for small transistors. So as a general guideline, you want to use high voltage devices economically, and only in locations where the high voltage capability is absolutely necessary. There are technological solutions to prevent or at least reduce substrate injection, but as usual, there is a price tag. If you're allowed to spend a bit more on your project, there's the option of using buried layers, creating isolating barriers in the vertical direction. This eliminates the drain to substrate diode and has a less effective substrate PNP, and in general gives much better control of parasitic currents. If your application needs a lot of high voltage devices, then you may want to consider using deep trench isolation. In such technologies, the lateral isolation is made with very narrow trenches that can be as deep as 30 micrometers and that are filled with isolating material. Although these deep trenches are very expensive, they have the benefit that they don't need guard rings anymore, and this can in turn save a lot of area. The most effective isolation technique is silicon on insulator, or SOI. In SOI technology, the devices are separated from the substrate by an isolating buried layer or box and surrounded by isolating trenches. As a result, all devices can have full dielectric isolation from each other which completely eliminates latch-up, leakage between devices, and makes this technology very suitable for operating at very high temperatures. Unfortunately, SOI is very expensive. It requires special wafers with prefabricated box and SOI layers, and because of the mechanical tension between these layers, the wafers are subject to warping, which limits the practical wafer size to 8-inch. Enough about technology. In the next section, we'll have a look at the defining characteristics and figures of merit used to compare BCD nodes. When dealing with high on-chip voltage and current, our first priority is robustness. We want to avoid damage or degradation. To achieve this, each device has to operate in the so-called safe operating area, as illustrated here. The safe operating area is demarcated by 3 limits. First, there is the maximum voltage limit set by the breakdown voltage of the device. In a robust design, the operating voltage should remain well below the breakdown. Second, there is the maximum current limit set by electromigration in the interconnect, but also current limits in bond wires. This limit is usually safeguarded by a protection circuit that shuts the device down if the current exceeds a safe level. And finally, there is a limit on the power dissipation that the device can survive. This is essentially a thermal limit and is time dependent. Usually, the operating temperature range for a device is specified, for example from -40 to 150 degrees C. Within this range, the device should be okay over its expected operating lifetime. When a fault condition occurs, such as an accidental short circuit in the application, the chip temperature can easily rise to 200 degrees C in milliseconds. In this case, the on-chip temperature sensor should shut down the device to cool off. If the device spends only milliseconds in this temperature range, this is fine, as long as it only happens occasionally. A device can even survive temperatures up to about 350 degrees C if this occurs for very short times. This can happen, for example, during hard switching transitions with inductive loads. I will explain about hard switching later in this tutorial. But if the temperature increases above 350 degrees C, then the device is likely to be destroyed. And this can be quite spectacular. This picture shows the remains of what used to be a 150 watt Class D audio power amplifier used in an application with poor supply decoupling. This actually caused an explosion in the lab with chunks of plastic from the package flying around. I already mentioned the breakdown voltage as a limit of the safe operating area. In practice, this limit is not so clear. First of all, the breakdown voltage is bias dependent. The off-state breakdown of a device is higher than the on-state breakdown. Furthermore, as can be seen in this graph, the on-state breakdown is kind of gradual. And before the device actually breaks down, it will start degrading. So, usually, high voltage devices have a maximum operating voltage rating that is significantly lower than the actual breakdown to guarantee the safe operation over lifetime. Another point of attention is ESD protection. High voltage devices need dedicated ESD protection devices. Shown here is a typical ESD device characteristic. The device turns on when the voltage reaches the trigger voltage and keeps conducting as long as the voltage does not drop below the hold voltage. The voltage across the ESD device increases with current until the device fails at the ESD voltage. The challenge here is to find a combination of high voltage device and ESD protection that fits the supply voltage in the target application. In many BCD applications, we use large DMOS power FETs as switches, which means that they are either switched completely off or completely on with the maximum gate source voltage and low drain source voltage. In this case, we are mainly interested in the lower left corner of the graph, where the device operates in the linear region. In this region, the drain current is described by these well-known equations, and the transistor behaves more or less as a resistor. Now we want to know the on resistance between the drain and source when we drive the gate with the maximum allowed gate source voltage. To do so, we could take the derivative of the linear region equation. However, unfortunately, the standard equation turns out to be a poor fit for high voltage devices because they disregard the effect of the drift region. So what we do in practice is bias the drain source voltage at 100 millivolts and measure the drain current at the maximum gate source voltage and then calculate the ratio of voltage and current. The on resistance depends on device size. When I connect two devices in parallel, I get a device with twice the area but half the on resistance. This means that the product of on resistance and area is constant for any device type. The product of RDS on and area is called the specific on resistance and is the most important figure of merit when comparing BCD technologies between wafer fabs, such as shown in the figure on the right. Specific on resistance scales with breakdown voltage and cannot go below a fundamental limit called the 1D silicon limit that describes the relation between the resistance and breakdown voltage in a theoretical, ideal, one-dimensional silicon device. This limit is shown as the bold red line in the graph. Beware that specific on resistance is determined at room temperature, but on resistance increases with the temperature. Besides the specific on resistance, it is also interesting to know the specific gate charge. This is the charge needed to turn a DMOS from full off to full on and is determined using the simple circuit shown here. Initially, the gate source voltage is 0 and the drain source is at its rated value connected through a high ohmic resistor. Then the gate is charged to the maximum gate source voltage through a gate resistor. The DMOS turns on and the drain is pulled down. The gate charge is the time integral of the gate current. This gate charge also depends on device size. When I connect two devices in parallel, both area and gate charge are doubled. So the ratio between the gate charge and the area is a constant, and this is called the specific gate charge. Specific on resistance is used to estimate the required silicon area to achieve a certain on resistance, which is associated with conduction loss. Specific gate charge can then be used to estimate the current consumption when switching that power fed at a certain frequency, which is associated with switching loss. Combining the two, we get a figure of merit that is area independent and is often used as a figure of merit to compare discrete power feds and different technologies such as silicon carbide and gallium nitride. In the next section, we're going to take a look at typical applications where BCD technology is used. Here's a list showing typical application areas for BCD technology with references to recent publications. The common denominator that connects most of these applications is that, one way or the other, they use power switches. Power switches can be categorized in low-side and high-side switches. In both cases, the switches are essentially solid-state relays. Low-side switches are used in applications where the load does not require an accurate ground, such as heating or lighting. And because the switch refers to ground, the control is pretty simple. High-side switches disconnect the supply from the load and are used when safety is an issue, such as in many automotive applications. But because the switch is now at the supply side, the control is more complex. And then there is the half bridge. What is a half bridge? It does sound like something that is not quite finished. However, in power electronics, a half bridge is simply a stack of a low side and a high side switch that can connect the output node to either the supply or the ground. Usually this is used to drive a load with some inductivity, and that can be, for example, an actual inductor or a loudspeaker or a motor winding. The switches are controlled with the break before make scheme to prevent them from short-circuiting the supply. And because of the inductive nature of the load, we need diodes to provide a conductive path to supply or ground when both switches are off. The term class D and switch mode are both used to describe the operation of a half bridge, and they essentially mean the same thing. But by tradition, class D is used for amplifiers, while switch mode is more common for power converters. Anyway, usually pulse width modulation is used to control the output node. In a nutshell, pulse width modulation is done by comparing an input signal to a triangular reference signal at a much higher frequency. This gives a square wave signal with a duty cycle that varies proportional to the input signal level. And after low pass filtering, we retrieve the input signal plus a small high-frequency ripple. With a half-bridge and an external inductor and capacitor, we can, for example, make a DC-DC buck converter. In steady state, the output voltage is proportional to the input voltage and the duty cycle of the switching node. And usually, the switching frequency is so high that the current through the inductor can be approximated with a triangle. With the same elements in a slightly different configuration, we can also make a DC-DC boost converter, where the output voltage is higher than the input voltage, and also here in steady state, the duty cycle controls the ratio. Two half bridges make up a full bridge. With a full bridge, we can, for example, make a Class D audio amplifier driving a speaker through LC low-pass filters. The PWM at both halves is such that the speaker terminals are driven with opposite phases. Perhaps now the term bridge starts to make a bit more sense. The load forms a bridge between the two output nodes. With a full bridge, we can also make a driver for electrical DC motors. In this case, the inductor is not necessarily an additional component, but can also be the inductance of the windings in the motor. Or we can drive an LC tank in a wireless power transfer system such as Qi, using one of these tailor-made coils. In this case, the frequency of the square waves is near the resonance of the LC tank to maximize the magnetic field near the coil, and this results in nearly sinusoidal currents. But why stop at two half bridges? Adding a third half bridge, we can make a three-phase power inverter that can, for example, be used to transfer the DC output power of solar cells to an AC voltage. Here the half bridges are switching with phase-shifted square waves, resulting in three nearly sinusoidal phases at the output. Or we can use the same configuration to drive a three-phase brushless DC motor in a similar fashion. Even more legs, how about a multi-level Class D audio amplifier, where the PWM signals are combined in a clever way such that the ripple currents through the inductors cancel each other to improve the electromagnetic compatibility. I could go on, but I guess you get the picture. The half bridge is the quintessential BCD circuit. So in this last section of the tutorial, I will zoom in on circuit design using the half bridge circuit as a vehicle. The power switches in the half bridge are obviously going to be implemented with power FETs, and these can be either external discretes or integrated on chip. In applications where the product of operating voltage and output current exceeds 1000 volt amps, it's probably better to use discrete power FETs. With discretes, it's possible to realize on resistances in the tens of milliohms range, and that would become excessively large in BCD. And you can use semiconductor materials such as gallium nitride or silicon carbide that have better specific on resistance and gate charge, but cannot be integrated on chip. However, even with discrete power transistors, the control IC will still be realized with BCD. When the product of voltage and current is less than about 400 volt amps, it becomes feasible to integrate the power FETs on the same chip as the control circuits, using DMOS, which is the focus in this tutorial. There are some challenges with high on-chip currents. The on resistance of our power FETs is finite, so when they conduct current, this will lead to power dissipation. Dissipation generates heat, and we need to incorporate the thermal behavior in our design to manage the temperature. Also, the switching operation causes fast current transients in the ground and supply lines, which in turn cause large voltage excursions because of parasitic inductance in bond wires, lead fingers, and PCB tracks. These voltage excursions can disturb other circuits or even trigger ESD protections. So this is why usually the half bridge has a separate power ground that allows some wiggle room with respect to a clean ground used for other circuits. High on-chip voltage also poses challenges on the design. As already mentioned, from a circuit design perspective, voltage becomes high voltage when it exceeds the maximum allowed gate source voltage. In that case, we have to take measures to prevent damage and limit voltage swings using voltage clamps or high voltage cascodes. Or we can use locally regulated supply domains, where we need to take special care of signals that cross domain boundaries and ESD path between the domains. Finally, we should be very careful with floating nodes, especially in low current, standby and power down modes. I will show you some general circuit examples to illustrate these topics. As explained earlier, high voltage devices are relatively large and expensive and should only be used when absolutely necessary. For example, in the circuit on the left is shown a current mirror with a straightforward high voltage DMOS cascode. However, the diode connected input device does not really need a high voltage rating. Instead, we could replace it with a low voltage device or use a different topology that is more area efficient. Now consider the circuit on the left where a high voltage DMOS cascode is placed on top of a low voltage NMOS. To enable low standby current, small pull-down transistors have been added to pull the gates to the ground, and this leaves the node in between floating. Now when the drain of the DMOS is connected to a high voltage, the leakage current through the body diode charges this floating node, and that can lead to damage in the gate oxides. This can be prevented by adding a clamp diode between the gate and the source of the DMOS or adding additional pull-down, as illustrated over here. Here's another typical case that can occur, for example, in the gain stage of an amplifier. If this stage is part of a closed loop system, then during normal operation, the gate to source voltage of the DMOS will typically hover just above the threshold. There is, however, nothing that would prevent the high voltage PMOS from pulling the DMOS gate all the way up to the supply and damage the gate oxide. This can occur during standby, as shown before, but also in overdrive cases when the closed loop system is forced outside its linear range. To prevent damage, we need to actively clamp the gate source voltage by using, for example, a Zener diode or a bypass transistor, as shown here. Now let's get back to the half-bridge circuit. Besides the power FETs, there are some essential elements that can be found in almost all half-bridge designs. First, we need to generate a voltage higher than the supply to turn on the high-side power FET. Second, we need gate drivers to charge and discharge the gates of the power FETs. Third, we need level shifters to communicate between the gate drivers and the low voltage control logics. And fourth, we need overcurrent protection so that we can take proper action if the current through the power FETs becomes too high. But everything starts with the proper design of the power FETs. The design target for power FETs is to achieve a specified low on resistance, which is coupled to conduction loss. The main contributor to total resistance is the intrinsic RDS(on) of the power FET itself. And we can make a first estimation of the required area by using the specific on resistance or RDS(on) times area product that I introduced earlier. But there is more. Because we are typically shooting for a low resistance target, the contribution of the interconnecting metal cannot be ignored. And on top of that, we need to be aware that the resistance increases with temperature. So first, let's take a closer look at the interconnect resistance. A typical BCD technology will have a 4 to 6 layer metal stack that can be either aluminium or preferably copper, because that has a lower resistivity. Usually the top metal is made ultra thick, as depicted on the right hand side, so it can handle large currents with very low resistance. To give you some ballpark figures, a typical ultra thick metal layer is 3 micrometers thick and has 6 milliohms of sheet resistance. In order to benefit from this ultra-thick metal, we need to follow some simple guidelines in the layout of the interconnect layers in between. This illustrates a typical power FET layout, folded 28 times in a drain-centered configuration. The vertical orange lines are the gates that are connected together top and bottom with horizontal metal lines to make low ohmic gate connections. The vertical blue lines are the alternating source and drain connections in metal 1. With the metal 2 layer, we make white perpendicular lines as shown here and connect to the metal 1 below with a checkerboard pattern of vias. This results again in alternating source and drain connections. And here you want to use the maximum allowed metal density and use as many vias as possible. The benefit in this way of connecting is that the metal 1 lines are now essentially split up into short segments that are connected in parallel by the metal 2. And in this way, the contribution of the metal 1 to the total resistance becomes negligible. Current only has to flow a very short distance through the metal 1 before it reaches the metal 2. For metal 3, we repeat the procedure. We make even wider vertical tracks and connect to the metal 2 with a checkerboard pattern using maximum vias, creating an alternating source and drain connections. And now the metal 2 lines are also split in short segments connected in parallel by metal 3, and making the contribution of metal 2 to the total resistance negligible. Current only has to flow a very short distance through the metal 2 before it reaches the metal 3. Then we arrive at metal 4, which in this example is the ultra-thick top layer. We repeat the procedure with the distinction that now we make tapered fingers that connect all drains together on the left and all the sources on the right, again using as many vias to the metal 3 as allowed. The benefit of tapering is that this yields a uniform current density in the top metal, and this results in a minimal resistance. Because the contribution of the lower metal layers has been made negligible by this connection method, we can approximate the total resistance of the metal stack with the sheet resistance of the ultra-thick top metal times the aspect ratio of the power FET. So in this example, that would be about 2.5 squares of ultra-thick metal, which is somewhere between 12 and 20 milliohms. If you want a more accurate calculation, there are resistive extraction tools that can also make fancy color maps that show the current densities in the interconnecting layers. But for those tools, you first need a finished layout, whereas the simple approximation can be done upfront as soon as you make your first draft floor plan. This shows an example of one of the papers in this conference where you can clearly see the tapered fingers in the top metal layer connecting the power FETs in the top half of the die. Now, as mentioned before, the on resistance of power FETs is temperature dependent. This graph shows the on resistance versus temperature normalized at room temperature. And as you can see, the on resistance changes almost a factor of 2 over the temperature range from -40 to 50 degrees C. So how can we determine the temperature? The flow of current through finite on resistance of power FETs results in power dissipation, which means it is converted into heat, and that causes the local temperature to rise. So what we need is a means to calculate how much the temperature of the chip increases. Depicted here is a schematic cross-section of a silicon die glued to a die pad of a package, and that is in turn attached to an external heatsink. The dissipation heat is generated in the PN junctions at the silicon surface and then flows through this stack towards the ambient, where the temperature is lower. This thermal system can be modeled with an electrical equivalent. In this equivalent, current represents the dissipated power and voltage represents the temperature. We can now build a thermal equivalent circuit as shown on the right, with a current source that models the power dissipation, a thermal resistance that models the heat flow, and a thermal capacitance that models the heat capacity. The ambient temperature is modeled with the voltage source, and the temperature difference between the silicon surface junctions and the ambient equals the voltage across the thermal resistance. With this thermal model, we can now set up an electrical thermal co-simulation, where the electrical circuit on the left is used to determine power dissipation and the thermal circuit on the right determines temperature. In principle, both models can run simultaneously to calculate the transient temperature behavior, but unfortunately not all simulators are capable of doing this. For example, if you use Spectre, the circuit simulator from Cadence, you cannot dynamically change the temperature of the devices. The alternative is to do so sequential iterations of electrical and thermal simulations until a convergence is reached. So now we know how to size the power FETs. Let's move on to the other half-bridge essentials. How do we generate the voltage to drive the gate of the high-side power FET? This is done with a technique called bootstrapping, and that works as follows. First, we take a look at the low side. The low side gate driver connects to a supply voltage VDDL refer to the power ground VSSP, and this automatically limits the gate source voltage of the low side power FET. The supply VDDL is usually generated with a linear regulator with an external decoupling cap. So when the low side power FET is turned on, the gate charge is drawn from the main supply through the regulator. At the high side, the gate driver connects to a supply voltage VDDH that limits the gate source voltage of the high side power FET. The supply VDDH refers to the switching output node Vout, and therefore it needs to track the voltage excursions of the output. And this is realized by using a charged external bootstrap capacitor as a floating voltage source. And the voltage across this capacitor is sustained as long as it is not discharged too much. And this is where the on-chip diodes come into play, that is connected between the low side and the high side gate driver supplies. Each time that the low side power FET turns on, the output node is pulled down to VSSP and the bootstrap capacitor is recharged through the bootstrap diode to a voltage near VDDL. This recharge current is provided by the regulator and drawn from the main power supply. Then when the high side power FET turns on, the output node is pulled up towards VDDP. The diode becomes reverse biased and stops conducting. Now the high side gate driver supply VDDH is lifted up to a level higher than VDDP and the gate charge to turn on the high side power FET is drawn from the external bootstrap capacitor. This will only cause a small voltage drop over the bootstrap capacitor because it is very large compared to the gate capacitance of the high side power FET. There are some interesting variations on the basic bootstrap. First of all, instead of a diode, you can also use an active high voltage CMOS switch, as shown here, that has the advantage that it eliminates the forward diode voltage drop and gives a better match between the low side and high side gate driver supplies. But how to control the switch? Well, that turns out to be not too difficult. The switch can be controlled by a latch consisting of two cross-coupled inverters that is supplied from the bootstrap cap. And next we add a high voltage PMOS as shown here in red that operates as a simple level shifter. When the low side power FET is on, the output node is low and the gate of the low side power FET is high. In this state, the latch node VA is pulled up through the body diode of the level shifter PMOS. This toggles the latch and turns on the bootstrap switch. When the low side power FET is switched off, the latch node VA is pulled down with the low side gate voltage until the latch toggles back and turns off both the level shifter PMOS and the bootstrap switch. Here's another interesting bootstrap variation. As said before, the bootstrap capacitor needs to be large because you want a small voltage drop when the gate charge for the high side power FET is extracted. But if you can allow a larger voltage drop, you can supply the same charge with a much smaller capacitor that can be integrated on chip. This circuit uses a secondary small high voltage bootstrap capacitor CHV. When the output Vout is low, this switch MHV is off and this CHV is charged up to VDDP. When the output node goes high, the switch turns on and CHV is discharged into C-boost with a large voltage drop, and that balances the gate charge of the high side power FET. And as a consequence, a regular bootstrap capacitor C-boost does not have to supply any charge and can also be made small enough to be integrated on chip. Another variation on bootstrapping is to use a charge pump in combination with a voltage regulator. The voltage regulator makes a supply rail VSSH that is negative with respect to the main supply and serves as an input voltage for the charge pump. The charge pump switches between two stages controlled by a clock. When the clock is low, the capacitor C-boost is charged between VDDP and VSSH through first diode, and when the clock is high, the capacitor is lifted on top of VDDP and discharged to the output capacitor through a second diode. And this generates a constant output voltage in VDDQ that is higher than VDDP. This is attractive in applications that use multiple half bridges, because the charge pump voltage can be shared by all, whereas if you use bootstraps, you need a dedicated cap for each half bridge. Now we know how to generate the drive voltage for the high side. It's time to have a look at the gate drivers themselves. The simplest implementation for the gate drivers is with inverters. We will assume that the low side gate driver is supplied from a regulator and the high side from a bootstrap. We are going to use this 6 transistor half bridge to analyze the dynamics of an output transition. We will use this analysis to figure out the proper sizing of the gate driver transistors. And for that we need to include the parasitic capacitors of the power FETs. First, let's explore what happens during a falling edge output transition when there is no output current. Shown in the graph are the output voltage and the gate source voltages of the high side and low side power FETs. We start with the high side turned on, with the gate pulled up to VDDH by the PMOS in the high side gate driver. The output is at the positive supply and the low side is turned off with the gate shorted to the source by the NMOS in the low side gate driver. The transition begins by toggling the high side gate driver and discharging the high side gate. When the discharge is finished, both power FETs are off and the output is floating. We have entered what is known as the dead time. And the term dead time is quite appropriate because during the dead time nothing happens. After the dead time has passed, we start charging the low side gate by toggling the low side gate driver. The low side gate source voltage rises until it reaches the threshold voltage of the power FET. At this point, the low side power FET turns on and pulls down the output. This causes the voltage across the gate drain capacitance to change, and as a consequence, all current going into the low side gate now flows through the gate drain capacitance, and the slope of the output is determined by driver current over gate capacitance. During the transition, the gate source voltage is stalled. The low voltage power FET can be viewed as an inverting amplifier with a capacitive feedback, which behaves as an integrator. The gate becomes the virtual ground node and the output is the integral of the input current. The same voltage slope that appears across the gate drain capacitance of the low side also appears across the gate drain capacitance of the high side, but with the opposite sign. Because the power FETs are identical, this means that the current that flows through the low side gate capacitance also flows through the high side, but in the opposite direction. This current is drained away by the NMOS in the high side gate driver, but pulls up the gate source voltage of the high side power FET. And needless to say, this only ends well if the high side gate source voltage stays below the threshold of the power FET. Otherwise, a shoot-through current would short-circuit the power supply. The PMOS in the low side gate driver is now essentially competing with the NMOS in the high side. This can be modeled by this equivalent circuit that contains both transistors fully on with their drains connected. To prevent shoot-through, the ratio of the NMOS and PMOS should be such that the output voltage of this equivalent circuit stays below the threshold of the power FETs. After the output transition is complete, the charging of the low side gate finishes and we're done. Please note that the dynamics for a rising edge transition are basically identical, but with the roles of low side and high side exchanged. A zero output current is in fact a rare occasion in a half bridge because of the ripple current in inductive loads. More likely there will be current flowing into or out of the output. So let's explore what happens when current is flowing out during a falling edge transition. This scenario is called soft switching. Our starting point is equal to that with zero current, apart from the fact that the output is now pulled below supply by the output current. Then the high side gate is discharged. However, before we reach the threshold level, there is a gate source voltage where the high side power FET will not be able to sustain the output current anymore. This gate source voltage is approximated with this expression that can be derived from the square law MOS model in saturation. At this point, the output slope drops as it is pulled down by the output current. This causes a voltage slope across the gate drain capacitor. Similar to the zero current scenario, all driver current is now claimed by the gate drain capacitor and the drop in the gate source voltage is stalled. The output slope is now determined by discharge current over gate drain capacitance. The high-side gate driver is actually slowing down the transition. And as explained before, the NMOS in the gate driver needs to be stronger than the PMOS. So in this situation, the slope is steeper than in the zero current scenario. And also here, the voltage slope that appears across the high-side capacitor also appears across the low-side, but with opposite sign. The resulting current flow through the NMOS in the low-side gate driver forces the gate below the source. Eventually, the output drops below power ground and forward biases the low-side body diode, and the discharge of the high-side gate can be completed. We enter the dead time, which is just as dead as it was in the zero current scenario. And now all that's left to do is charge the low-side gate. The low-side power FET turns on and shorts the body diode. However, because the current is still flowing out, the output voltage stays below the power ground. In soft switching, the output current pulls in the same direction as the intended output transition. The opposite also occurs, and this is called hard switching. In the hard switching scenario, current flows into the output. This means now that in the starting condition, the output is higher than the supply. Again, the transition begins by discharging the high-side gate. However, this time, the output current forward biases the high-side body diode and the output voltage rises. We enter the dead time and we wait and wait a bit more, and then we start charging the low-side gate. When the gate source voltage reaches the threshold, the low-side power FET starts conducting, building up drain current. And because the output current is fixed, an increase in drain current through the low side means a decrease in current through the high side body diode. We now have the strange situation where current is flowing in both high side and low side power FETs at the same time. Note, however, that this is not a shoot-through current, since these currents have opposite directions. Anyway, the low side gate voltage rises further until the drain current in the low side matches the output current. At this time, the current through the high side body diode is zero. Before we continue, we need to understand something about diodes. When a diode is forward biased, electrons from the N side, where they are majorities, cross the PN junction to the P side, where they are minorities. In other direction, the same happens with holes. Overall, this means both sides of the PN junction are flooded with minority charge carriers. When the voltage across the diode is reversed, these minority charge carriers flow back to where they came from. This means that at first the current also reverses direction. This reverse current continues until all minorities are back where they belong. This mechanism is known as reverse recovery, and it is characterized with reverse recovery charge, which is the total amount of minorities, and the reverse recovery time, which is the time it takes to return the minorities to where they came from. Bottom line is this: when you reverse polarity across a forward biased diode, this does not mean the current stops immediately. Now, back to our half bridge. After the body diode current reaches zero, it simply reverses direction and starts increasing in the other direction. This adds to the output current, and now we do have a shoot-through. The low side gate source voltage at the peak of the reverse recovery current can again be derived from the square law MOS model. Now note that at this moment, the drain to source voltage of the low side power FET is nearly equal to the supply voltage, while at the same time the drain current is the sum of the output and the reverse recovery currents. This results in an extreme high power dissipation in the low side FET. For example, in a half bridge with an 80 volt supply and 12 amps of output current, this peak dissipation can exceed 1 kilowatt. This dissipation only lasts for tens of nanoseconds, but since the half bridge is usually switching with a frequency near the megahertz range, the contribution to the average dissipation is still quite significant. Anyway, after the reverse recovery time, the reverse recovery current drops abruptly to zero, leaving only the output current. The gate source voltage of the low side power FET has overshot its target and pulls down the output node at an excessive rate. This causes the gate source voltage to drop until a new steady state is reached, where the slope is determined by the low side charging current and the gate drain capacitance. As before, the gate charge current also flows through the NMOS in the high-side gate driver and tries to turn on the high-side power transistor, but this is prevented by correct scaling of the gate drivers. And finally, the low-side gate charging finishes and the output settles above the power ground. Shown here side by side are the output and gate to source voltages of the power FETs for hard switching and soft switching scenarios. And as you may have noticed, in both scenarios there is a dead time where nothing happens and can actually be considered a waste of time. So as it turns out, you can actually skip dead time altogether without creating problems, as long as the gate drivers are sized properly. Instead of using simple inverters, the gate drivers can be a bit more complex, as in this example. In this gate driver, the size of the pull-up and pull-down transistors is adjustable, depending on whether we're in a soft switching or a hard switching scenario. This is done to slow things down when necessary and speed things up when possible. Also, during hard switching, gate discharge of the power FETs is delayed as long as the current flows in the reverse direction. This results in an essentially negative dead time and is done to prevent current flowing through the body diode, and this effectively eliminates reverse recovery. Here's an example of a gate driver that works together with a constant charge pump voltage instead of an external bootstrap cap. The high-side gate driver has an integrated bootstrap that biases the gate of a DMOS source follower that serves as a local supply for the gate driver inverter. When the power FET is turned on, the charge current from the inverter is multiplied by current mirrors and supplied from the charge pump. This example is used in a 5-channel multi-phase Class D audio amplifier, where instead of 20 external bootstrap caps, only 2 external caps were needed for the charge pump. Next topic on our list is the level shifters that are essential in communication between the gate drivers and the low voltage control of the half bridge. In general, a level shifter is a circuit that transfers logic signals from an input to an output voltage domain. The output domain can be at a positive or a negative level with respect to the input, and it can be static at a constant or very slowly changing level, but also dynamic and fast changing, such as the high side gate driver of a half bridge. Level shifter operation needs to be robust and insensitive to disturbances, because miscommunication between gate drivers of power FETs can lead to destructive failures. A very simple means of level shifting is with a capacitor that essentially provides AC coupling between the input and output domains. Capacitive level shifters are very fast, nearly instantaneous, and also they are impartial to the voltage difference between the input and the output domain. They work equally well for positive and negative voltages. Finally, apart from the capacitor itself, no high voltage devices are needed, so they can be quite compact. Of course, there are also some limitations. First of all, in a capacitive level shifter, there can be no signal gain. The voltage swing at the output domain is always smaller than at the input because of the loading of the capacitor. Also, to prevent the top plate voltage from drifting away, we need to define the DC voltage with the biasing circuit, and the regular activity is required to maintain signal integrity. This makes a capacitive level shifter unsuitable for static signals, such as, for example, trimming bits. Finally, capacitive level shifters are sensitive to voltage transients. A transient on the output voltage domain cannot be distinguished from an input signal transition. Here's a practical implementation of a capacitive level shifter that uses a differential configuration, where 2 capacitors are operated with inverted phases. At the output, a cross-coupled latch is used to fix the low signal level to the local ground. This type of level shifter is popular for level shifting clock signals, such as in this example, where a differential capacitive level shifter drives the switches of a high voltage input chopper in a capacitively coupled instrumentation amplifier. The output domain voltage level is coupled to one of the input terminals, and this allows a common mode range from -30 to +30 volts. A level shifter that is also suitable for static signals can be made with a single DMOS at the input and a resistor in the output domain. When the DMOS is off, the resistor pulls up the node, making a logic 1. And when the DMOS turns on, it pulls down the output node, making a logic 0. This configuration only works if the output domain voltage is positive with respect to the input, but a complementary version can of course also be made quite straightforwardly. In this level shifter, there are no floating nodes, so this is suitable for both static and dynamic signals, but the voltage swing of the output node is sensitive to PVT variations. Also, current flows as long as the pull down is active, and this results in a trade-off between speed and power. For high speed, the pull-up resistor should be made small, but this then requires a large pull-down current to make sufficient voltage swing. Here's an example of a very fast static level shifter used in a high-frequency DC-DC converter. It uses two DMOS pull-downs operated with inverted phase. The voltage swing at the output nodes is limited by using non-overlapping clamps that have a deadband in the middle of the output domain, and a comparator is then used to decide the logic level. Thanks to the differential operation, this level shifter is insensitive to voltage transients in the output domain and is especially suitable to connect to the high-side gate driver of a half bridge. In this example, the voltage swing of the output domain is 50 volts, with a propagation delay of less than 5 nanoseconds. The swing of the output node can be fixed when we match the pull-down current to the pull-up resistor, as shown here. When the DMOS turns on, the pull-down is defined by the current mirror in the source. And a simple trick to speed up the transient behavior is to add a small gap in the source of the DMOS that causes a short current spike at turn on. This shows an example of a level shifter in a biomedical application that uses a feedback loop to regulate the voltage swing in the output domain. The difference amplifier forces the voltage across the dummy pull-up resistor equal to the output domain supply. The pull-down current from this feedback loop can then be shared by multiple level shifter channels, making this a very area-efficient solution. In this last level shifter example, the output nodes connect to a latch that consists of two cross-coupled inverters, and two DMOS pull-downs are used that operate with inverted phases. In this configuration, the high voltage PMOS transistors are inserted in the pull-down paths that turn off when the corresponding branch is pulled down. The advantage is that there is no DC current but only short current spikes during transitions. And this is a nice feature if the output domain is a high-side gate driver that is supplied from a bootstrap capacitor that would otherwise be discharged by the DC current. However, this is a tricky circuit that requires careful dimensioning of the devices to guarantee proper operation over PVT corners. And it is also relatively expensive because it requires 4 high voltage devices for a single signal. This brings us to the last topic on our essentials list, the overcurrent protection. Overcurrent protection is essential to prevent damage in half bridges. There are 3 protection strategies that can be used after an overcurrent is detected. First is latch off. In this case, the system shuts down and only restarts after an explicit reset. This is a good strategy in applications where fault conditions can cause safety hazards, such as in industrial environments or cars. Second is the hiccup mode, where the system shuts down but tries a periodic restart to check if the fault condition persists. This strategy is often used in switch mode power supplies. And third is a cycle-by-cycle current limiting. In this case, the system continues operation, but the duty cycle of the half bridge is modified such that the current stays below a safe limit. This kind of protection is popular in audio amplifiers, where a short overload should not cause annoying interruptions known as audio holes. All strategies have in common that first of all, somehow the overcurrent needs to be detected. And there are 2 main approaches to do this. One is to use a series resistor, which is accurate but also introduces additional power loss. For overcurrent protection, high accuracy is not necessary, So usually the second approach is used, where the drain source voltage of the power FETs is compared to that of a small matched replica. So how does that work? A replica FET is a transistor of the same type as the power FET, but much smaller. The ratio N between the replica and the power FET can be as high as 1 to 10,000. The replica and power FET have their gates and sources connected and need to be matched as good as possible, both in geometry and temperature. The replica is biased with the reference current, and a comparator is added to compare the drain voltages. The overcurrent flag goes high when the current through the power FET is N times the reference current. Note that this scheme is only accurate for positive currents that flow from drain to source. If the current flows in the reverse direction through the body diode, the current distribution is not homogeneous, but tends to crowd in the hottest part of the diode. As explained in the first part of this tutorial, DMOS transistors have a fixed channel length, which means that only the width can be used for scaling. Power FETs are very big. A gate width of 10 centimeters is not exceptional, and typically many folded fingers are used in parallel. The replica, on the other hand, needs to be small to get a high ratio, and this results in poor matching. A simple technique to improve the matching is to build the replica as a stack of devices. This gives a higher ratio and also improves the matching because a larger area is used. The comparison of drain voltages only makes sense if the power FET is turned on, which means that the gate source voltage is maximal and the FET is operating in the linear region. In this situation, the drain source voltage is small and can be applied directly to the comparator input. But when the power FET is off, the drain source voltage can be very high. In fact, it can be so high that it could damage the comparator and we need to disconnect it with a switch. This can be done quite elegantly with this circuit that combines the function of a switch and a voltage divider. The gate of the replica FET and the bottom switch FET are always on, with their gates connected to the maximum gate source voltage. In the off state, the top switch FET is also off and the internal sense node is pulled low. In the on state, both switch FETs are on and divide the drain source voltage of the power FET by 2. And this adds an additional factor of 2 to the ratio. If we apply this scheme around the low side power FET, the signals during an output transition look something like this. When the low side power FET is off, the output node is high and the sense voltage is pulled low. Then the gate of the power FET is charged. During the transition, the output gate voltage stalls above the threshold, and this means that the top switch FET also starts conducting a little, but not enough to pull the sense voltage up by much. Only after the output node transition, the gate of the power FET finishes and the sense voltage settles to half the drain source voltage of the low side power FET. If the sense voltage is higher than the reference voltage, the overcurrent flag is raised. The voltages that appear at the input of the comparator are low with respect to the power ground, and this makes the comparator design fairly straightforward. It can be made without using high voltage devices. And we can use this exact same configuration around the high side as well. In this case, the reference and sense voltages are still small, but now with respect to the half-bridge output. The comparator design is the same as the low side, but it is now supplied from the external bootstrap capacitor. This does mean, however, that a high voltage level shifter is needed to transport the comparator output to the low voltage domain. And besides fast, this level shifter needs to be insensitive to voltage transients because it connects to the half-bridge output. On top of that, we need to be careful with capacitive couplings to sensitive nodes, such as the reference current source. An alternative is to build a comparator that is supplied from a static voltage and disconnect the inputs when the high side power FET is switched off. This can be done by inserting 2 DMOS switches between the comparator inputs and the sense and reference voltages. These switches can be controlled easily by the gate of the power FET. In the off state, the comparator inputs are clamped to the supply with diodes, so the common mode swing is limited. And this again leads to a straightforward comparator design followed by a high voltage level shifter that in this case does not have to be insensitive to voltage transients since it connects to a static voltage domain. And in case we have a charge pump instead of an external bootstrap capacitor, the implementation becomes even simpler. By connecting the gates of the replica and the top switch FET to the charge pump, they are always on. This means that the reference and sense voltages are always close to the supply and no clamps are needed to limit the voltage swing. This brings us to the end of this tutorial. As is usually the case with tutorials, I have only scratched the surface of this subject and many topics have been left out because we only have limited time. However, if you want to hear more, I recommend these papers from this year's ISSCC. Not surprisingly, most are in the domain of power conversion, but this year we also have a session dedicated to audio amplifiers. And here's a list of references for further reading. Thank you very much for watching this tutorial. I hope you found it useful. If you have questions, please join the live Q&A session on February 20th at 8:40 a.m. PST. Goodbye.